It's recording. We had done, at least introduced, pretty much all the stuff about resistors except for the equation to do resistance as a function of heat. So what I'm going to do now is I'm going to work on a couple of problems so that we've got the problems started, and then we'll probably start, if we don't start it today, we will definitely start it on Wednesday, which will move us into the next chapter, because she does it all in the next chapter. So one thing, again, where we were talking, is that it's not a big issue. It's getting into us into the, it's going to get out of the way. It's getting us to the point of understanding how we look at the underlying part of this and give us into our the understanding of how we're getting current in the first place. So this one is, we've got a drift velocity, and drift velocity, remember, is not really an actual thing where we're moving this electron out the other end. Remember, we're doing a series of collisions, but because we have that series of collisions, we ultimately are going to get an electron out the other end. And it's going to appear much like water going through a garden hose. So if I've got the drift velocity of free electrons, and we're going to use copper, and it's going to give us at 7.84 times 10 to the minus 4 milliseconds, we want to know what is the electric field in our wire. We want to know what electric field is going to produce this drift velocity.
And that's milliseconds, right?
No, that's meters per second.
Oh.
Yeah, it's times 10 to the minus 4, so it would be 78 milliseconds, but it's on times 10 to the minus 4. So what we're going to do is we're going to look at the flow. And remember that force on an electron, which is causing the flow in the first place, is mass times acceleration. Electrons aren't going to move unless they've got an acceleration associated with it. So I'm going to rearrange this and solve for acceleration. And so I've got force divided by the mass. And if I look at my force in terms of electric field, that's Q times my electric field divided by the mass. And this is one of those places why they suggest that physics 1, you have it before you have physics 2. But again, it's one of those cases of, you can kind of pick this one up, is we have the velocity final is equal to velocity initial plus acceleration times time from my kinematics equation. Now, when we're looking at this and we're looking at the electric field is going to cause the movement, the initial velocity we can assume to be 0. So my final velocity, which is now the drift velocity, so to speak, okay, that's our drift velocity, is going to equal the acceleration times time. Now I've already solved for acceleration, so I'm going to put my Q, E, M, and now I have time. But time's kind of interesting in this case, because my flow, we know the flow is a result of the cascades, and so we're actually going to use a different variable here. We're going to call it a tau, and we're going to see tau a couple more times over the course of where we're headed. We're gonna get that. But tau is really, what this is the time between collisions. So that's going to be a time between collisions. And the other thing about it is this is dependent on the material. And if you think about it, that kind of makes sense. Copper atoms are going to be different than iron atoms, which are going to be different than vanadium, which is going to be different than silver, which is going to be different than calcium. And so we get this time between collisions. It's going to depend on the size of the atoms and the number of electrons per unit volume. So we're going to get something that's inherent to the material. So I'm going to rewrite this as Q, E, M, and now I have a tau. And I'm going to go back at this point and relate it back to current, because I got to deal with this time, because right now I've just got a drift velocity, I have no time, and so I've got to kind of come back and relate it back. So this is one of those weird stepwise problems that you got to kind of know where you're starting and you got to kind of know where you end up to get there. So current, we saw, was the number of charges, their speed, times the area. And we just now got our final speed, so I can put that in. So I've got the number of charges, Q, E, M, tau, per unit area. And I'm going to rewrite it a little bit. But in this configuration, if I look at current density, that's current density. And if I take I divided by A, that's why I get this, because if I do that, I get current density. This becomes I divided by A. Now, I can go to a table, and conductivity, which we've kind of already seen, is NQ squared tau, mass of the electron. Or resistivity is mass of the electron, NQ squared tau. So they give us this in the problem because we can look it up for copper. So I'm going to look up copper's resistivity, and that's 1.7 times 10 to the minus 8 ohm meters. If I do that, I'm going to solve for tau here. So tau is mass of the electron, number of charges squared, resistivity. Yeah, to the minus 8. Do what? You guys good?
Yeah.
Okay. So now, if I take V final is equal to Q, E, tau, mass, this becomes Q, E, mass, mass of the electron, rho, Q squared, number of electrons. Masses cancel, one of the Q's cancels, and the drift velocity becomes E rho Q, number of electrons. I want to solve for E. E is equal to rho, number of electrons, Q, V. This was given in the problem. Q is my electron. We can look up rho for copper. And now my only problem is how many electrons are there. And you can do N is equal to Avogadro's number, the molar mass of copper, times this is the density, not resistivity. Okay? And so N will give you 6.02 times 10 to the 23rd. And that's the number of atoms. And we get 8,920 kilograms meters cubed for copper. And it's 0.0635 kilograms per mole. Gives me the number of electrons is going to end up, or the number of atoms is going to give me 8.4 times 10 to the 28, and that ends up being over my volume. And so E is going to be 1 times 10 to the minus 8 ohm meters, because that's my resistivity. My 8.46 times 10 to the 28 meters cubed, number of electrons, times my charge, which is 1.6 times 10 to the minus 19 coulombs, times the drift velocity, or the velocity that they gave me, and that equals 0.18 volts per meter. Killing 2 markers today. Unlucky for you, A, a problem like this will not be on the test. B, it's showing you that you can figure out the electric field in a wire. We will need that a little later because an electric field creates a magnetic field creates an electric field, and that's what's going to give us current. So we're going to see that down the road. But the whole idea behind this is underlying the whole issue is those free electrons are free to move, which is going to allow me to get current. That's why copper is a good conductor, white silver is a good conductor, and because when you start looking at this and you look at how this works, for copper, this electric field is very, very small. But for calcium, it's not going to be all that, it's going to be a lot harder because calcium's not going to have as many free electrons to play with. And so getting these collisions to actually give us flow is really what we're after. So then, for those of you who want to go to the electrical engineering piece, this is the underlying why we get the equations we get. And so it's just a matter of, you'll see this again, and you have to have it shown up another way. All right, so we're going to fabricate a wire from 1 gram of copper. Okay, so we're going to start out with 1 gram of copper. And the wire is going to have a resistance. So it's going to have a resistance of 0.5 ohms. And we want to know the length of the wire and the diameter of the wire. Because in this case, we're making our resistor instead of our resistors that we can buy off the shelf, we're gonna make it. Remember, if I go back and I look at where we were last week, I get resistance is resistivity times the length divided by the area. And I'm gonna have resistance divided by resistivity is gonna give me my length per area. Area is going to equal pi d over 2 squared. We'll get there in just a second. So let's go ahead and figure this part out. The resistance I have to have is 0.5 ohms. I look up the resistivity of copper, 1.7 times 10 to the minus 8 ohm meters. That's going to give me 2.94 times 10 to the 7th 1 over meters. Density of copper is going to equal 892 kilograms per meter cubed. That's my density of copper. If I do density is equal to mass per unit volume, and volume, in this case, I've got mass, and I have volume is length times area. So I'm going to solve for area instead of doing that way. I'm going to solve for area. I'm going to get area is equal to mass density times length. And length is going to equal mass density times area. And we now have L over A is equal to that ratio. So I'm going to do this one first. I'm going to do length first. So length is equal to 2.94 times 10 to the 7th area. So if I plug this in, 2.94 times 10 to the 7th area is equal to the mass, which was 1 gram. So I got to do 0.001 kilogram. The density, which was 8,920 kilograms meters cubed. And then I have area. So area squared, 0.001 kilograms, 8,920 kilograms meters cubed, 2.94 times 10 to the 7th, and that was 1 over meters. Gives me 6.23 times 10 to the minus 8 meters squared. And if I do, that area is now pi d squared over 4. D ends up being 2.8 times 10 to the minus 4 meters, or 0.28 millimeters. And then depending on how you want to do it, you can take the square root of this, plug that back in, and L ends up being 1.8 meters. That pin, told you, we kill pins today. And we talked about resistance heating. And I'll bet there were several of you this morning that wanted a resistance heater going on, because at my house it was 43 degrees this morning, outside. On the inside it was about 66, which was fine. It's good sleeping weather. But resistive heating becomes important. So my resistor, this gives us the function of temperature on resistance. So this is my nominal resistance, 1 plus alpha T minus T0. This is my temperature coefficient for the material. And you can just go in and find out if I've got we'll just do one for copper. The coefficient for copper happens to be 3.9 times 10 to the minus 3, 1 over degree C. So if I start out with a piece of copper wire that has a resistance of 10 ohms, I want to know what the new resistance is and T is in degrees C. So if I go from, let's go from 20 degrees C to 30 degrees C. It's going to be 1 plus my 3.9 times 10 to the minus 3. And I've got 30 degrees minus 20 degrees. My resistance only increases, this inside here becomes 1.039. So my resistance only increases by 10.39 ohms. But what happens is I start to heat up, I get more resistance. I start to heat up, I get more resistance, and you will ultimately get a lot higher resistivity. So let's do a length of copper wire. So I've got a length of copper wire that is 34.5 meters long at 20 degrees, has a radius of 0.25 millimeters, and we have a 9-volt battery that's applied to it. First thing we want to know is what is the current. And then we want to know what happens if we're at 30 degrees. So copper, again, resistivity for copper is 1.7 times 10 to the minus 8 ohm meters. My coefficient for copper is 3.9 times 10 to the minus 3, 1 over degree C. We've got Ohm's law, V is equal to IR, and we have R is equal to rho length divided by area. We're given length, we're given the diameter, or no, this was a radius. We're given the radius. So I can calculate the resistance. So the resistance is going to be 1.7 times 10 to the minus 8. 34.5 meters, pi r squared. And the trick is that this is 0.25 times 10 to the minus 3 meters. My resistance ends up being 3 ohms. So now I've got I is equal to V divided by R. 9 divided by 3 gives me 3 amps. Now I just plug in this one. So now I have my 1 plus my alpha, which is 3.9 times 10 to the minus 3. My change in temperature is 30 minus 20. And this ends up being 3.12 omega. But guess what? Over the same current, I is going to be 9 divided by 3.12. I now drop my current down to 2.9 amps. Okay, most of you, I don't know if you know it or not, what's your circuit breakers rated at for a household circuit?
Each breaker.
Yeah,
Mine, I think, is 15.
you got 15? Some are 15, some are 10, some are 20, you know, and then some are 30. Like your air conditioner will be on a 30 amp breaker. Some like your dryer, if it's an electric dryer, will be on a 20 amp breaker. You'll get some interesting breakers. So let's do one here. We've got a waffle iron. And a waffle iron is rated at 1,000 watts. And our normal voltage in the house is nominally about 120 volts. Okay? Because we use 60 hertz, it's 120 volts. So we've got that. And we want to find the current through the waffle maker, and we want to find the resistance through the waffle maker. So power is equal to I squared R, which is equal to V squared R, which is equal to IV. So I'm going to do power divided by the voltage is going to give me the current. It's 1,000 watts divided by my voltage, which is 110 volts, 8.3 amps. So if you have a 15 amp breaker and you got 2 waffle irons going, guess what's going to happen to your breaker? It's going to have to rip it. Now if I want to know resistance, resistance is V squared divided by P. I'm going to take my 120 squared divided by my 1,000 watts, and it's going to give me a 14.4 ohms. But this is the key issue for resistance heaters. And if they kick on at the same time, you're popping breakers. And I can't have my air fryer on one of my circuits in my house. I can't have my air fryer or my toaster oven and my microwave running at the same time. It's just not going to work. Just not going to work. And then you can do the other. So we'll take a DVD player. It needs 350 milliamps at 6 volts to run. We want to know the power required. I've been given current, I've been given voltage, so I'm going to use PV, or P is equal to current times voltage. So you get 350 times 10 to the minus 3 amps times 6 volts, 2.1 watts. Okay, we good? Alrighty, we're gonna dive into the next topic. Which moves us into circuits. So, essentially we have two ways of producing a current. Okay, we've got two ways of producing a current, and we're gonna see it in a little bit, because what happens is, have a magnetic field and an electric field, they're gonna interact, and we're gonna actually be able to produce a current. But we can produce the current, but at this point, we're not gonna talk about how we get there, but we can talk about it in terms of where we're gonna get our source, okay? So we can get current using a battery, or a DC power supply, and then we can get current from what we do is alternating. Oh, God, I can't spell today. We get alternating current. So if I'm using a battery, this gives us something we call direct current. And this is giving us our alternating current, which is what we're getting out of the wall. We're going to start with DC current because it's easier to look at and play with initially. And in this case, we have a steady state. We have a steady state for the current, and the current is always in the same direction. AC current doesn't give us that, but DC current does. And we've talked about it so far. I can have a circuit, and in case of DC, my flow of electrons is positive to negative, and I'm always showing my electron flow. Now if I look at my battery, we can think of the battery as a store of charge, right? You can think of the battery as a store of charge. It's got a positive and negative aspect to it. And it's going to be our source of charge. Now, I've told you over and over again that learning physics, you kind of have to learn history along the way. And so it's an artifact of history that the potential difference on the battery, so between my positive and my negative on a battery, is called EMF, electromotive force. There's not a true force. It's not a true force in the sense that we think of forces. But if we think of this as a charge pump, you can kind of see how somebody might call it a force. And so, but this is really related to our good old electric potential. It's not a force, it's electric potential. But the thing about our batteries is that the battery is inherently a device. And inherently, my battery is going to have, its own internal resistance. So for true batteries, we usually refer to this as the voltage that we get from a battery is our electromotive force minus the current that's going through there, and this little r is the internal resistance. And you know you get an internal resistance because if I take a 1.5 volt battery, a C battery, and I put it in the circuit, what happens to my battery after time? What happens to my phone if I'm talking on it a long time? Well, the battery starts to die, but what else happens?
It's hot.
It's hot. I've got an internal resistance. So my batteries will heat up, and that's one of the issues that you have with some of the other batteries. I've got two issues, by the way. One of them is that why they don't want you to have your lithium batteries out there is because everything on my, if you think about it, and I'm building smaller and smaller devices, if I use my 12-volt battery in my car, those cathodes and anodes are far apart, right? But if I look at my battery, my lithium ion battery, and you look at it, you know, the little charge plate, there's your cathode and there's your anode. And if I've even got a whisker of something across the way, I've created a circuit. Guess what happens? My battery starts to drain, it starts to heat up, and if I'm in a suitcase on a plane, it has a tendency to warm up and start a fire. Okay? And resistance heating, you know, don't store incompatible materials. Okay? I can take any battery, particularly a 9-volt, our fun little 9-volt batteries. Fun little 9-volt batteries, you've got to watch what you've got your little 9-volt batteries touching. Because if I get something across there, guess what happens? I complete the circuit, it starts to heat up, and I can create a fire. So you gotta watch where those things are, because I do get that internal resistance. So if I'm looking at my circuit, okay, if I'm looking at my circuit, remember I can draw a switch. I have my voltage here. Here's my lovely circuit. When the switch is open, current is equal to 0. And my voltage for my battery is going to be equal to its electromotive force. Or we can call this the open circuit voltage. Now when I close it, current's no longer there, and now I get the current through the system. The resistance of the system is equal to whatever my battery is supposed to be minus whatever is going to be in my internal resistance of my battery. Now, most of the time we build our circuits where R is much, much greater than my little internal resistance of my battery. And so we get to see what we've been seeing before, and then IR is equal to my electromotive force, which gives us back Ohm's law. Okay, gives us back Ohm's law. But again, that's what happens. But a lot of times we're going to have a couple of little problems that we have to figure out the internal resistance of our battery. So let's look at our batteries, our systems in series. So if I have a voltage and I've got my first resistor and I've got my second resistor and I've got current coming through here. All right, so this is R1 and this is R2. In this system, I've got current. Current's going to go through R1. The current's going to come out here, and it's going to go through here. And so the current through the system is going to equal everything going in there. And we've already done it. The voltage supplied by the battery is going to equal the change in voltage across 1 plus the change in voltage across 2. And this becomes IR1 plus IR2. And this becomes IR equivalent. Those I's all cancel. And for resistors in series, I get that they add up. And you've already done the measurements. Should have already seen it. Now, if we do it the other way, where I have things in parallel, when I get to this spot, the current has a choice. So if this is I coming in, current has a choice going out and splitting up. So I have current 1 and I have current 2. And when I come back in over here, I still have to have this same current going that way, but these things are coming in a little differently. This is R1 and this is R2. And you can use a water analogy that gives us a split. But my I at this point is going to equal the current that comes in from the first side plus the current that comes in from the second side. And I can get that my voltage is equal to this, and my voltage 1 over R1 plus my voltage 2 over R2. And we've already seen that if I looked at from here to here, my voltages are the same, so the voltages cancel out, and I get 1 over Req is equal to 1 over R1 plus 1 over R2. So this is for parallel, this is for series. But this is going to become very important to us. Extremely important to us. This right here, we're going to call a node. Okay? Or a junction. And this becomes the junction rule. Oh, can't really spell today. That becomes the junction rule. This one, we can look at it and look at it as a loop. So we're going to get a junction rule and a loop rule. So what we've got is we've got, for series, Req equals R1 plus R2. For parallel, 1 over Req is equal to 1 over R1 plus 1 over R2. The junction rule says at any junction, the sum of the currents must equal 0. Okay? The sum of the currents must equal 0. And then I'm going to have my loop rule. And we're going to get that in just a little bit. Because I'm about to lose Enid. And these gets us to Kirchhoff's rules. And we're going to start looking at our circuits and our loops. And that's going to get us into our equations. So we'll work a lot of problems on Wednesday. We'll start with Kirchhoff's rules. And that gets us in pretty good stead. Now, what day did I say we were doing the testing here? Did I say we're doing a test in here?
We just took one like last week, so I don't think so.
Well, we're ready for a test.
It's on that.
Not do it on Friday.
We're ready to, well, the thing is, I need to get us a test so that I can give you the take-home portion of the test for the loop rules and stuff. So I'm guessing we probably want to go ahead and have a test over, and the test will be over doing equivalent capacitance, power, equivalent resistance, because we want to do that. And then I always do the loop ones as a take-home, because it's not fair to try and have you do it in an hour. Because if you pick the wrong loop, it sucks up all your time, because it gets hairy, and you guys will see that in a little bit. So I'm guessing what we're going to end up with is a test on Monday, which will be the 14th. And then I will hand out the take-home portion on the 16th, so that you have the whole fall break weekend to bring it back on, but you'll have time to do it ahead of fall break though. See, that's the good part. And then we'd have it back on the 21st. Okay, so the test will be the 14th. And then the take-home portion will go out on the 16th. Okay.
And the test on the 14th is gonna be over what?
It'll be over doing things like the capacitors and getting equivalent capacitance. It'll be doing, well, we're gonna start with resistors, doing some resistance. Will not have drift velocity. I don't, and that's just mean, cruel, and wicked. And you know, I'm bad enough, so I don't wanna do that. But it'll have that part of stuff on it. It'll have doing power and charge on a capacitor, power and charge across capacitor, that kind of stuff.
Okay.
And the same similar stuff over resistors. But I won't do full-blown resistor circuits. That will be the take-home part.
Okay.
Because the resistor circuits will, that gets messy. And so we want to make sure that we're covered on that.
Perfect.
And power on both cases, power for capacitors, power for resistors.
Are we gonna have a practice test for that?
I'll see.
I'm glad it's just not on Friday.
You know what it
I
is?
got
Pick
all
all it up.
weekend. I may not have a weekend.
I don't have blackboard up.
I may not have one.
Yes, sir.
3 hours.
Yep.
Well,
I got a note saying that I need to resubmit it.